Hey guys, happy rainy but maybe nice and warm later on Friday. This is section 5.2, confidence intervals using normal distributions. Now first a word about chapter 5. I should have mentioned at the outset of chapter 5, and that's that this is the one chapter that was completely restructured when they went to the second edition. So unfortunately a lot of the things that I had prepared for the first edition don't quite apply in the same way for the second edition, so I've had to sort of try to adjust on the fly when I went to the second edition so that you could access Wiley Plus. So I hope you'll be a bit forgiving if if I'm leaning heavily on some of the publisher materials here for this section. But I am going to show you how to do the things that they're doing with StatKey with R to make the connections that we'll need for where we're headed. And also I'm hoping that with all the materials that you have that you'll be able to feel pretty comfortable with this material. And when I say that, I mean at the section 5.2 hub there's the interactive lecture, which will parallel what I'll do. We'll say probably a little bit more about StatKey than I will, because I want to show you at least one or two ways to do this stuff in R. Alright, but first, before we get into the new ideas, I want to sort of set the stage for what we're doing. Back in chapter 3, when we dealt first with bootstrap distributions, the standard error method for the bootstrap confidence interval was this, right? The statistic plus or minus 2 times the SC, and we were making use of the 95% rule, kind of the empirical rule, to do this. Now in chapter 5 what we're doing is we're staying in this 5.2 section, we're staying with the statistic, and we're staying with the standard error coming from the bootstrap distribution. Yes, I know that can stand for other things. But what we're going to do is figure out a way to recalibrate the 2, right? I mean, the 2 comes from the 95, so you might have guessed that the bell curve is at the the root of all that. So what we're going to do is generalize this and see that we can pick a standard normal value, and we'll see that the value, and I'm giving you a quick preview here, spoiler alert, if we want to be P level of confidence, there's a Z star and a minus Z star that we're going to find that will be the right multiplier to use. But the standard error in our transition stage is still going to come from the bootstrap distribution. So we're going to admit that that procedure might not quite fit as we move on to the more classical case, I guess, where we have a series of intervals such as like p hat plus or minus a something, and an x bar plus or minus a something, and maybe even something like an x bar 1 minus x bar 2 plus or minus something. And we'll see what the pieces should be in those particular cases. All right, and that'll lead us into the formula-based classical approaches. So let's get started with the work for today. And there we go. Confidence intervals using normal distributions. So first we'll take a look at a motivating example here. This is the honeybee waggle dances. Now you've seen this before in regression when you were trying to predict distance from the length of the waggle dance. That is, if you were one of the bees. If you were the one doing the dance, then I suppose the prediction problem was how long to dance given the distance. But let's take a look, just to kind of enrich if you're not familiar with this.
Honeybee workers are able to send complex messages to one another. In the wild, they sometimes nest out in the open, but mankind has persuaded them to live and store their honey in hives. The colony's heart is its queen. She is just a little bigger than her subjects and mother of them all. In spring, when food stocks are low, the workers get busy collecting nectar. They have a remarkable method of telling one another where to find the most productive flowers. It's called the waggle dance. This returning bee has just found a new source of nectar and is going to tell others in the hive about it. First, she gathers an audience. To do that, she climbs on her sisters' backs and vibrates her abdomen. Now that she's got their attention, she begins her dance, using a code of movements that tell her fellow workers where her discovery lies. The duration of her waggle indicates the distance to the nectar source. The longer the waggle, the further the flower. And the angle at which she dances across the comb tells them the direction to the flower in relation to the sun. Her instructions are remarkably accurate and can pinpoint the location of a nectar source over 6 kilometers away. Some of her fellow workers set off immediately to find it. In one short season, the colony's workers will visit up to 500 million flowers and will make around 90 kilograms of honey. That is sufficient to sustain the whole colony through the coming winter when there is no nectar to be had.
Okay, well, I'm hoping that won't keep this video from getting bounced from YouTube, so we'll see. If you have any problems accessing it, please let me know. Now, you may think, all right, the first time they did the waggle dance, they had it right, but apparently there was an earlier and less successful version of the waggle dance. But you might want to take a quick look at that before we go on.
I'm going to sing you my little song about my little thing that I entitle The Bee. What a glorious thing to be, a healthy, grown-up, busy, busy bee, making hay while time is ripe, building up the honeycomb just like tripe.
Okay, well, you can take a look at that on your own time and see what you think about that. But anyway, before we get into that, I just want to give a quick shout out to the Pollinator Habitat Enhancement Project. So if you haven't looked at that already, please take a look. Let's see, I've got a link to this, yes. We'll see what your classmates are doing, or maybe some of you are involved in that. The Pollinator Habitat, very nice website that Nikki's put together. And to explain some of the projects, I've been spending a lot of time out there. There's the past and the present. Trevor and Amy have been in biostats in the past. Nikki's in the current class. I don't know what Nico's excuse is, but no, anyway. But some beautiful pictures that Nikki's done. Wanted to share that with you in case you haven't seen those. All right, so sorry, Nikki. I thought I'd... well, hopefully you appreciate that, but didn't mean to embarrass you. So hopefully I haven't violated any license agreements there. Okay, so just to review in case you skipped through the video, honeybee scouts investigate new homes and communicate the information with a waggle dance. The scientists took bees to an island with only 2 possible options for nesting in this particular study, one of very high quality and one of low quality, and they recorded the quality of the nesting site, the distance to the nesting site, the number of waggle dance circuits performed, and the duration of the waggle dance. Okay. So how does the number of waggle dance circuits performed differ by quality of nesting site? So we can take a look at the data. Now actually I have it open in RStudio. So let's see, in the RStudio Cloud link that you have here, let me just double check that this brings to the right space. And it does. The problem is it's going to boot me out of the other one in case you've ever seen I think one of these is going to give me disconnected, but anyway, let's not worry about that. So in the files section, what you're going to be looking for here is the section 5.2 lesson. There's also an activity that I'll be recording separately, but the section 5.2 lesson is what I'm going to walk you through here. Take a look at the bees data. Let's see up here. So what we want to do first is run the upper information, and I did a quick reordering of the categories so that what I do here is going to match what you would see if you either use StatKey or what's in the slides from the publisher. So how does the number of waggle dance circuits performed differ by quality of nesting site? So I'm doing a box plot. Oh, and by the way, this is a different data site than used for regression. This is the Honeybee Circuits data set that comes with Log5 data. And if we run that, we get a plot, and we're comparing the quality high versus low and the number of circuits. So we see quite a different distribution. For high, it's quite a high number with quite a bit of variability there. But the question is about the difference in means. So let's go ahead and compute our statistic. Okay, here it is. So I use favstats. It's jumping around on me a little bit. I use favstats to look at circuits by quality. So I get quite a big difference in the mean. But the question is, with all the variability in the data, is that going to be significant? But actually, our main question is to try to estimate the difference in the mean number of circuits. So we're really focused on a confidence interval rather than a difference in means, because it does look like a pretty dramatic difference. Now, first step would be to compute the statistics. So we get the 60.49 to 2 decimal places, and we'll be ready to move on towards a confidence interval here. So just to kind of make the connection between the slides and what I've got in the R code for you to take a look at. So we've estimated the difference. So we're thinking confidence interval, and we're thinking bootstrap confidence interval first. And so here's how you would do it with StatKey. Now my results in R are not going to align exactly. I'll do 2,000 samples like they did. I would encourage you, if you're sort of curious how much difference the simulation is making, to run it a few times and just get a sense of how stable it is. To review, for the bootstrap confidence interval, we use the resample and the groups equal. For the categorical, here's the quantitative variable. The name here, bootstrap mean, is what we're going to use when we graph it. I'm not showing the head command to look at the data. I just wanted to streamline this, but the variable that we're going to bootstrap is actually called diff mean, and that's what we'll use to get the standard error. So as a reminder, let's see, so that created the now it's finished. It created the bootstrap. The histogram is here. It's centered at the sample statistic that we saw was around 60.49. So that's where it's centered, roughly. Approximately. This parentheses around here, just as a reminder, is my way of outputting the value but also saving it to an SE. So adding, saving it to a variable called SE. Adding the parentheses at either end is going to, it's going to output it. Otherwise, you wouldn't get the output. You'd have to put it on a separate line to print it out. So, and then to calculate our confidence interval using the bootstrap, as I said at the output, we're starting with this plus or minus 2 SE for the 95% interval, so we can get the lower and the upper if we run the whole thing at once. We'll get the output here, and if we knit it, we'd get it all there. So we've got the lower endpoint and the upper endpoint. There's a way to make this more concise and give both, but it's not worth the complication probably for us. So 26.7 to 94.2 is pretty close to what's showing up here. You might be bothered by the little bit of difference, but if you run that another time and wait for the 2000, you'll see that there is some instability in this, right? This time I got 27 to 94 roughly, so it lines up pretty well here, and these are in fact equivalent. Alright, so just a reminder, the idea if we were doing the percentile interval would be to chop off in each tail. So that would be another way to calculate the interval. Okay, so we're computing the statistic plus or minus twice the standard error to get the interval. So let's see, if we wanted to get the percentile interval, we can also do that, and I want to do that to align with what we had, right? So we'd use CData, we'd use diff mean, and we'd use P equals 0.95. We want to line up with the 95%, so what was it? P equals 0.95, and data equals, data equals bootstrap dot mean in this case. So what we're using, I think that's what I called it. Oh, I should have called it diff mean, huh? Let's make a quick fix here, and you'll forgive me because you'll see it. I'm gonna leave it, because if I change it now, then I'd need to restart, otherwise it would be confusing. So we'll leave it at that, and go ahead and get the interval, 29.8 to 95.3. So that's actually perhaps a little bit closer. So we've got the percentile interval. Maybe there's a little bit of skewness due to the skewness in the distribution, but both of these are methods of bootstrap confidence intervals we've considered, but we're going to focus in on the statistic plus or minus 2 standard error approach for what we're going to be looking at and for the extension that we're going to be making. Now, before we move on, just a few facts about these bootstrap distributions. As a reminder, bootstrap distribution is centered at the sample statistic, so in this case at the difference in means. It has standard deviation equal to the standard error of the statistic, right? The standard deviation of the bootstrap is how we get the standard error. And if it's normally distributed, thinking about normal distributions, we can write it this way. Because it's centered at the sample statistic, it has a normal shape, and it has a certain standard error that we've computed from the bootstrap. So we could actually take a look at that. Now, for the purposes here, let's just take a look at it in StatKey here. We've got in this simulation, the mean was 60.736, standard error was 16.38. So you could go ahead and plot a smooth curve, the normal distribution, and then kind of remove the details, taking advantage of these facts about the distribution, and then just focus on the normal distribution itself. So we're going to find the middle p% of the normal distribution to get the confidence interval. So in this figure in StatKey, they're using the confidence interval procedure in getting that. Now I'm just going to show you at the command line how you could do this with R, kind of set the stage for what we're going to be doing. And there's a command called xcnorm that will give us the middle portion of the normal distribution, so exactly parallel to what StatKey is doing. So we'll put in 0.95, and we'll put in mean equals 60.49, and standard deviation equals 16.38, and we get this confidence interval. We get the middle 95% and then 5% on either side. So we get the endpoints 28.38, 92.59. Exactly paralleling what you'd get if you use the normal distribution under the theoretical distribution in StatKey. Alright, now there's a little bit more detail. Remember, that doesn't output when you knit, so when you knit you would just get those two values if you use this xcnorm. And we will use the xcnorm for the standard normal very shortly. Okay, so to continue from there, this is the same idea as the bootstrap. We're just sort of smoothing things out and using the theoretical result that these bootstraps for a reasonably large sample will often have a normal distribution, and we're going to take advantage of that to get our confidence intervals in a more streamlined way. So here's the logic of where we are so far. We start with a bootstrap distribution, and we sort of replace that with a normal distribution with the statistic, which is the original statistic, and then the standard error which is the endpoints, the standard error that we get from the bootstrap distribution. Okay? And that led to our confidence interval by taking the middle 95%. Now, remember I said that the whole point of this section and exercise is to move from a t, from a 2 corresponding to 95% to sort of generalize that. And that generalization is going to, one, give us a connection to the idea of a theoretical distribution, which is where these formula-based methods come from in Chapter 6, and to let us generalize the standard error method of confidence intervals to something other than 95%, to a more general probability. Okay, so here's where this is coming from. Remember the process of standardization back in Chapter 2? And we saw it with the hypothesis test in 5.1. We can think of unstandardizing or backward standardizing by starting from the standardized scale, and to unstandardize we're going to rearrange that and solve for x rather than z. So we rearrange and then we solve for x. So we get the mean plus the standard value times the standard deviation. We're going to use that idea of taking a standard value and we're going to generalize that for the confidence interval. So in testing we go to a standardized statistic. That was the statistic minus the null over the standard error. For confidence intervals we're going to find the minus z star and z star, right, the multipliers that I was talking about over here, for a standardized distribution, and then return to the original scale through the confidence interval. So we'll take the mean plus z times the standard deviation, but what's the equivalent for the distribution of the statistic? It's going to be the bootstrap distribution. So let's have a look. The process will be to take the statistic plus or minus the z star times the standard error, where temporarily the standard error is going to come from the bootstrap distribution. So to summarize, we've got this p% confidence interval that we want, and we're going to try to find the appropriate z star and minus z star that have p% in the middle. So we want to find the values that capture the middle p% of the normal distribution, and then return to the original scale by that unstandardizing, right? We're multiplying by the standard error, adding that to the statistic, and that will give us the idea of a confidence interval using the standard normal. So the basic, kind of the nutshell of this approach in Chapter 5 is that if a statistic is normally distributed, right, we bootstrap it, we can see it's normally distributed, we find a confidence interval using the statistic, the standard error, but our multiplier is the z star that's going to correspond to the level of confidence that we want. All right, so let's see how we could get that. Before we get into the specific example, let's just take a look back over here at the R code. So what I wanted to show you was if we take, let's say, 0.95, XC norm 0.95, and we're going to get 95% confidence interval. The right multipliers are actually 1.96. The z star, that's the upper value, negative 1.96 for the lower value. These are kind of the numbers in the Statistics Hall of Fame. 1.96 is the multiplier corresponding to 95%. So you can see the 2 that we've been talking about all along is really an approximation, right? The exact value for 95% would be 1.96. If we wanted 99% confidence, we'd have to increase that multiplier, right? Because the intervals would have to be wider to contain 99%, to contain the parameter 99% of the time. So it gets expanded out to 2.58. 2.576 is actually the multiplier. If we were happy with 90%, in some cases we might want a narrow interval, but we're okay if it's only right 95% of the time, then the right multiplier is 1.645. So you can see that this process of enclosing a certain level of confidence is going to be an effective way to get the right multiplier to use with our interval. All right, so we're going to use that principle to go ahead and return to our bees, still happily waggling away, and we're going to use that to get a 95% confidence interval. So we're going to use the sample statistic from the original value, original data, get the z-star from the standard normal, and use the standard error from the bootstrap distribution. And now I wanted to lay out the steps in the slides here, but let's go ahead and do it live and see what we get. And it won't be exactly the same as what shows in these slides, but you'll have the process on RStudio Cloud for carrying this out. All right, so the command xcnorm is going to show us the values. All right, let's see, if I run this whole thing, I will get the output as well. I was looking for the output, maybe it was down below, but the xcnorm is giving us, it's giving us the figure and the two multipliers, but really I only want the positive one. So the trick for doing this in R, well, I'm fine if you do it manually. Instead of you see that there are two values and you pick the 1.96, the positive one. The trick is to put a square bracket after, and then that'll just pick up the second one. So you can do it either way. It's fine with me. But then I use two separate lines for this. So the statistic, let me rerun this whole section. Oh, I see. I jumped down to the next one. It's jumping around a little bit on me. So anyway, the endpoints that I get with the statistic plus or minus the 1.96 are 27.66 to 93.31. And remember, that's going to change. So if I rerun the lines above, I'm letting that run, and then I rerun this chunk, that's going to be a little bit different. The interval I get this time is 27.5 to 93.5, but those are all pretty plausible values. So the confidence interval that we get here in the notes is 28.4 to 92.6, very similar to the kinds of things that we're getting here. All right, but that's the process. So we're using the bootstrap to get the standard error from up above. We're using the standard normal to get the right multiplier, and the statistic is the original statistic. It's never the mean of the bootstrap distribution. It's the original value that we had way up here as the difference in the means, right, when I first computed it. So don't lose sight of the fact that that's where the statistic is coming from. Right, now we can expand that to a 99% interval rather than 95 just by putting that in. We're using the larger multiplier of 2.576. So of course we get a wider interval, and that's the endpoints to the interval that I get in that particular situation. All right, so pretty straightforward, I hope. Now whether you kind of see the whole process, that might take some time to think through, but we start with the bootstrap distribution. We're replacing it with a smooth curve with a 95% in the middle that kind of justifies the process. And we sort of drop the mean and the standard error of the standard normal, and move to the idea. Sorry, I think I misspoke. What I was saying is we're replacing the bootstrap distribution with the normal with the same mean and standard error. But then we use that kind of to see that with this process of unstandardization, what we really just need are the multipliers corresponding to the level of confidence. So we move to the standard normal for the sole purpose of grabbing that multiplier, that z-star value that we need. And then we unstandardize. The method is statistic plus or minus taking that z-star to get an interval. All right. Okay. So middle 95%. If we wanted another level of confidence, we'd pick another middle percent. And I've already shown you the 99% interval in R, so I think we're ready to move on and summarize. Okay. So why use the standard normal? Z-star is always the same regardless of the data, so we don't have to run the simulation to get the value of z-star. We're just using it to get the standard error. So the Hall of Fame, as I was saying, at 1.96, it's approximately 2, but in general we'll use the 1.96 to be more precise. And then these other two are the most common confidence levels. Although if I asked you for a 97% interval, I'd want you to be able to find that. You could use the XC norm or even the C norm without it. I'll show you in a minute, just to get the multiplier for that particular case. Alright, so one more example, and then we'll be in a position to wrap things up with the lesson portion, and I'll turn you over to the activity and the example. So syntaxes, this is a sample, so we're going to be looking at a proportion rather than a mean. This is a random sample of 1,000 U.S. adults asked about, do you favor or oppose syntaxes on soda and junk food? Maybe eating out would be up there as well, but this one was just about soda and junk food. So 320 adults responded in favor of syntaxes. So they favor them. So we're wondering what proportion favor these. And we want a 99% interval. So we can go ahead and do that in R. And I will show you how we would do that. So I've got that down below here. So we'll do the bootstrap of p hat using the rflip command. Remember, you use the sample proportion. We use the n, but you don't have to access the data itself. For the one sample case, we're just simulating it by flipping a coin. So we run that. We can take a look to make sure that it does fit with this idea of a fairly smooth normal distribution. I didn't worry too much about the breaks here, but let's see, bin width is 1 over 1,000. Let's see, that looks pretty good. I think I got that right. And then our standard error comes out to be 0.015 roughly, or sorry, 0.015, yes, that's right. So then we can use our statistic. Our p hat is 320 over 1,000. I just wanted to call it statistic to parallel things with what we have up above. Z star, we can get, so I said in the comment that we're leaving off the x because all we really want is the multiplier, and I'm grabbing the value in the second place, so I want the positive value, and I put the parentheses on so when you run it you're just going to get the output, and then the statistic, the upper and lower. So if we run the whole chunk together, we'll get the values. And let's see, what did I do wrong here? Oh, I forgot to change that to a plus. Alright, so let's see, that looks a bit better. The 0.28 to 0.36 seem reasonable. And if we ran this one more time and then ran this, we'll get a slightly different interval. Did I not get a different interval? Let's see. Yeah, there we go. Alright, it changed a little bit, but it was quite precise. Alright, so just to move on to the wrap up, if a distribution of a statistic is normal, then we can go ahead and compute the confidence interval this way. From the original data, we get the sample statistic, we get the z star from the standard normal, and we're getting the standard error from the bootstrap distribution. But at this point, we have to admit that wouldn't it be nice if we could compute the standard error without having to do all those thousands of simulations, even though it's pretty quick. But to streamline the process, we can, or at least we'll be able to next class. So as we move into chapter 6, we'll be talking about inference for proportions, for means, so we'll have specialized formulas that come from the underlying theory that will allow us to compute the standard error directly. And then we can focus on checking conditions, that the conditions are satisfied for carrying out the procedure, and then also focus on the interpretation. It'll still be used for resampling methods like bootstrap and randomization, but those will be especially useful when we're working with statistics that don't have nice distributions or known standard error formulas. And I've certainly used those in practical settings as well. Alright, I think we'll wrap this up here, and I'll see you over in the activity and the examples screencast. Take care and thanks for listening.